Hello everyone and welcome to today's webinar where we'll be looking at transformer technology and how it can help reduce your electricity use and energy bills. My name is Stephen Kennett and I look after the built environment and energy channels here at 2 Degrees. I'm delighted to welcome our presenters today. We have Erica Wilson, Managing Director of Wilson Power Solutions, who has a wealth of experience in this area. Joining us from Tesco is Bob Granger, Technical Standards Manager for Electrical, who will share with us how they have saved 9 million kilowatt hours per year through reduced transformer losses and improved voltage to site. We're also very fortunate to be joined by Steve Young, an independent power management consultant. Today's presentations will last for around 45 minutes, which will leave us with 10 to 15 minutes for questions at the end. Before we begin, I'd just like to remind everyone that you can submit questions throughout the webinar using the Q&A box on the bottom right-hand side of the screen. Just type in your question and press send, and then we'll wait till the end before answering as many as we can. As an aside, if you should have any technical issues during the presentation, please use the chat box on the right-hand side to send me a message, and I'll get back to you as soon as I can. So without any further delay, I'd like to hand over to Erica, who'll get us started with today's presentation. So over to you, Erica.
Thank you very much indeed. Good afternoon. Thanks very much for taking the time to listen today. My name is Erica Wilson. I'm the Managing Director at Wilson Power Solutions, a company based in Leeds. So over the next 10 to 15 minutes, I will explain how distribution transformers are often overlooked when, in fact, they are silent consumers of energy. I'll also explain how super low loss amorphous units can help improve the energy efficiency of small distribution networks and illustrate how much energy and perhaps more importantly the costs you could save in your business with this technology. So looking at the agenda for today, firstly, why do transformer losses matter at all, and how can we mitigate these losses? The amorphous technology behind mitigating those losses, and then of course the additional savings that can be made through the inbuilt voltage management capability of the transformer. And finally, I'll discuss the new Wilson E2 with the on-load tap changer, which addresses fluctuations in the incoming supply voltage at site. So why do transformer losses matter at all? Well, staggeringly, roughly 3% of all electrical power generated worldwide is wasted through transformer losses. Just let's look a little bit closer to home here. There are around 4.6 million distribution transformers installed in the EU. Now their combined losses exceed 38 terawatt hours per year. If you put it into perspective, it's actually more than the annual amount of electricity consumed by Denmark, and it equates to 30 million tonnes of carbon dioxide. So we saw this as a market opportunity for a product that would help reduce all of this unnecessary waste. There are two types of energy losses when a medium voltage distribution transformer is live. These are load losses and no load losses. Now, the load losses depend upon the varying load of the transformer, but the core losses are fixed. So as long as the transformer is energized for, it could be perhaps 7 days a week and 365 days of the year. I must say at this point, through experience with all our customers, not everybody realizes that when they're metered at medium voltage, they're paying for the losses within their own transformers. And actually, in years gone by, everybody was aware of transformer losses, but it was very unusual for a customer to request particularly a low-loss transformer. Maybe the reason could be down to the increased price of the product in the first place, and also the relative low cost of electricity at that time. I think contracts were won then upon the upfront contract price, rather than now today's long term of longer return on investment. It's a different view now. What we did was we set out to create the UK's first super low loss transformer. Now the Wilson E2 is the first distribution transformer in the UK to combine two energy efficiency approaches, combining amorphous metal cores with low current density conductors. The unit's losses are reduced by up to 75% in the core. And as a rough guide, cut overall transformer losses in half, making the E2 the most energy efficient transformer available in the UK. There have been efforts to improve energy efficiency of transformers over the years in Western Europe and the US. So-called low-loss units would offer those reduced load losses through use of conductors with a greater overall surface area. And also in countries where supply infrastructure is notoriously unstable, like India, efforts to reduce core losses permanently actually led to the development of core materials with better energetic profiles, such as amorphous metals. So the actual meaning of the word amorphous is Greek for shapeless. So you can see there on the slide on the right hand side by its molecular appearance. And in basic terms, amorphous core material is far more easily magnetised than a standard core steel, and that's due to this random molecular structure. So the structure of it means that less friction is created during that magnetisation, and so therefore less heat is produced, which results in those lower losses. You can see again on the infrared imagery there at the bottom where the CRGO standard core steel unit shows a far greater heat in the red colour on the left than the amorphous product on the right hand side. So let's now look at the process for amorphous core manufacture. Compared to conventional CRGO core manufacture, it's really very much different. Now, amorphous metal is an alloy in the form of ribbon, so it's a tenth of the thickness of a standard core steel at 0.025 mil. So there are only 3 standard widths available from Hitachi Metals in the USA, and the width of material selected actually depends, of course, upon the design of the transformer. But as the material is actually extremely thin, it means it's not really possible to cut it into small lengths. So what we do is we combine 10 sheets together and then cut them into lengths. And once the cutting is done, we form into loops, and then the annealing process is done to retain the magnetic properties, and then finally a resin will be applied. Looking at these images here, the top left shows you that core loop we've just described, and then below where the HV and the LV coils have been fitted. So you can see in that image on the right hand side the LV bars protruding there, and on the left the HV leads come out. So once that core coil assembly is complete, the image in the middle shows the construction with those HV leads coming out and leading off to the tap changer, the HV tap changer. Now the whole construction is clamped at the top and bottom. On the far right there, I've shown a shot where the transformer has been fitted inside the tank and covered with oil. So this is the final stage of manufacture. And on the left of that image you can see there the LV bars connected to the 4-pole LV monoblock, which goes out through the tank to the LV airbox, which contains the cables. And then there are 3 HV bushings there on the right, connected up, that go out to the HV airbox. Amorphous core assemblies are actually very short and fat in appearance compared to a standard construction. So you might think that it's actually a waste of oil there, that top expansive tank with oil in it. But actually, the reason we did that was that we were meeting IEC standards upon design and cable heights of the transformers. So we did that so that obviously when you're retrofitting a transformer you can swap one out for the other and use your existing cable boxes. Let's just have a look here at this loss comparison chart. So it shows loss values for a typical 1000 kVA transformer, and it compares a conventional standard CRGO transformer with the second generation of the Wilson E2. So as you can see, the combined losses for the CRGO units there are just under 14,000 watts, and those for the super low loss amorphous are just over 7,000. So roughly speaking, losses are halved, as we'd said earlier, in the Wilson E2. But in terms of actual energy savings, the super low loss unit saves over 33,000 kilowatt hours per annum, which is over £3,100 per year, and we base that on a tariff of 9.5p per kilowatt hour. It's important at this stage just to note that there are currently no industry standards classifying super low loss transformers. So as a purchaser looking into buying a low loss or a super low loss unit, it's really important to ask for loss values, perhaps create a table and compare them with competitors out there in the marketplace. So let's just recap here. A super low loss transformer will provide you with guaranteed savings through those reduced transformer losses. So a 1000 kVA unit will typically save £3,100 per year, which equates to a lifetime saving of over £77,000 through the loss savings alone. But the savings through the reduced transformer losses are not all. In addition to those guaranteed savings we've discussed, as a result of those transformer losses, many customers and clients can realise substantial additional savings through voltage management or voltage optimization, as is known, at no extra cost. What the units are designed to do is deliver the required site voltage, and in addition they come with an extended tapping range as standard. The following additional savings that can be achieved through voltage optimization are dependent upon the load profile of your site. So what I'd actually recommend is to advise for a full survey to be done to assess this suitability, to have a look at your different load profiles, which are voltage dependent and perhaps which are voltage independent. In a nutshell, the transformer will be designed to deliver the required site voltage without any need for additional downstream equipment. So really you've got a two-in-one solution, and it minimises plant footprint, and so you avoid those additional system losses, including cabling from any other pieces of equipment. Now you can expect up to 12% saving on your energy bill by doing this. But we do appreciate, of course, that site supply can fluctuate, that's incoming site supply. So we do offer a product with an automatic on-load tap changer, which has an AVR relay which allows you to fix the output voltage when necessary. Now this high voltage on-load tap changer is dynamic, and it has 17 positions, which allows you at single phase to adjust your voltage in 2 volt steps, so between 215 volts to 254 volts approximately. And many people of course talk about 220 volts as the optimum voltage to site. Now with the AVR relay that comes with the unit, your commissioning engineer can set the tap changer to change between 30 seconds and 3 minutes. So dependent on your voltage profile and fluctuation into site, you can set it accordingly. So of course, at night time, when typically your load drops and the voltage may jump up, your tap changer is there, of course, to just bring that voltage back to the 220 mark. So naturally, you're maximising your savings from keeping that 220 volts to site. So to date, we have over 400 successful client installations, and just listed here you can see a few more results where clients have retrofitted their own transformers for the Wilson E2. So we do supply across a wide range of sectors, from hotel chains, as you can see, food suppliers, and the retail sector, to name a few. So I hope today I've given you a bit of food for thought Thank you very much indeed for taking the time to listen, and I'll hand over now to Bob.
Thank you, Erica. My name is Bob Granger. I'm an electrical engineer working for Tesco, and I'm going to give you a short presentation on where we as a business currently stand with regard to energy savings and the bigger carbon challenge, and also what has led us and how our experience of working with WPS and the use of their E2 transformer and how it has contributed towards energy savings. So, the challenge. We've declared that we're going to become a carbon zero business by 2050. We're going to cut distribution emissions per case of goods delivered by 25% and halve building emissions per square foot compared to 2006-07 by 2020. So how are we going to do this? Well, we have a three-tier strategy. Number one, energy efficiency. We want to reduce the amount of energy we use, and this is our overriding and key priority. Number two, reducing HFC leakage from our refrigeration systems and replacing HFCs with lower emission alternatives or natural refrigerants. Number three, using renewable energy where appropriate. We've trialled various technologies: solar panels in Thailand, combined heat and power in the Czech Republic, ground source heat in Hungary. In 2012-13, our carbon footprint was approximately 5.75 million tonnes, and approximately 65% of this figure was related to our electrical consumption, which obviously shows how key energy efficiency is and its associated impact on our carbon footprint. Successes so far. Okay, we've got a couple of headline statements here. Firstly, energy efficiency. We're now saving approximately 270 million a year globally. We've also opened over 10 million square feet in the last 5 years without any net increase in energy consumption. During 2012-13, we managed to reduce our refrigerant emissions by some 6% compared to the previous year. We also realised it will not be enough to just focus on our own emissions, and back in 2009 we also gave ourselves an objective to reduce the carbon footprint of products we sell by 30% by 2020. We've just completed a piece of work that has identified approximately 2/3 of product emissions come from just 139 high-impact products, in particularly laundry goods, meat and dairy. That's a staggering statistic, and we are now actively targeting strategies in association with our suppliers of what can be done to make our processes greener for these particular products. So, where and what to do? Well, obviously renewables. We are constantly reviewing new and evolving renewable technology. Have trialled numerous instances of these, but continue to view these, particularly the main players in this field at the moment: biofuel CHP, gas CHP, ground-sourced heat pumps, biomass boilers, roof polycrystalline and thin film PV, solar wall, solar thermal, wind. Now this is by far not an exhaustive list, but these technologies are constantly improving and becoming more viable, and we continue to monitor them closely. We have intended, and we currently this year are planning major expenditure on energy-led initiatives that will and are forecast to provide us with a 110 gigawatt-hour part-year saving effect. That's a huge saving, most of which is related to conversion from T5 lighting to LED. LED has come on a lot in the last few years, and the improvement in technology has led us to a point where we are doing a lot of conversion work. Also, CO2, natural refrigerants. This is now a standard for all our new stores and is a big part of the plan to reduce carbon consumption due to its GWP index of 1 when compared to 3,300 for R0404A, which is the most commonly used refrigerant in our stores. Every little helps. It's a good catchphrase and one that we are known for. We run our transformers at high load factor and fairly constant load, so any improvement we can get in regard to losses are worthwhile. Add to this the fact that we have over 1,500 HV sites in the UK, and this is most of which operate in 24/7, and the energy benefits are obvious and cumulative. A little bit of history now. Transformer history. Prior to 1990, we as a business did not have a defined engineering specification for transformers. We were predominantly led by the contractors, and they supplied, in essence, whatever they wanted in terms of product. We had no defined specification in terms of construction or losses. So, move forward to the early 1990s. We developed and introduced a specification, and obviously part of that specification we did dictate and state minimum core losses. These losses equated to somewhere between standard and low loss in terms of current day technology. At that point, the transformers were still supplied one by one or on an individual project basis by the electrical subcontractor. Move forward to 2002, 2003, and for the first time we decided to tender our annual transformer requirement in the form of a package. This was done, and obviously individual transformers were then pre-issued to the contractors on a job-by-job basis. Obviously this resulted in better value from a commercial point of view for us and better control of the distribution and lead times on these products. During this time, we were in partnership and set up framework agreements with a number of leading suppliers in the transformer field. South Wales, Transformers, Brush, Schneider Electric were all involved in term agreements during this period. 2009, another tender exercise, and we again looked at renegotiating with the existing suppliers. At this time, Wilson's obviously were a key consideration here, and we moved into a framework agreement with them based upon the amorphous E2 copper with extended tap range. Approximately 18 months later, we moved to actually adopt the E2 aluminium. From a commercial consideration, this was obviously beneficial to us. Since 2009, our relationship with Wilson's has worked well, but it was put under strain in 2011. At this time, we as a business declared that we would open 3 million square feet of new sales space. This was something we'd never aimed for before, and it was approximately a 1 million increase on anything we'd ever done in any development year previously. This put massive strain on all our suppliers in terms of what they had to produce and the lead times, or should I say lack of lead times they were given. All our suppliers struggled with this, but nonetheless they all came through. From a transformer perspective, a shipping incident closed the port of Mumbai, which effectively embargoed a large quantity of transformers which were due to be shipped to the UK for us. This caused some problems, but they were overcome, and the bottom line was, during that year, all stores opened on time. So, the results. We're currently saving over 9 million kilowatt hours per annum. Now this figure is made up of obviously improved core losses, but also the ability to fine-tune the voltage setting because of the extended tap range available on the E2. This in turn is saving us over 2,000 tonnes of CO2 per annum. And from a reliability perspective, no failures. Of the 90 E2s installed, we've had no issues. So looking ahead, what's in the future? Well, as Erica spoke about earlier, there's the E2 Plus with auto tap changer. This is something we are actively keen to trial and are planning trial installations in 2014-15, and we're hopeful of the results we're going to achieve. So, in summary, we currently have over 90 super low loss transformers in the business. We're getting good payback and good benefits from these, and our relationship has worked well with 0 failures. From a business perspective, we're happy to recommend the Wilson E2 transformer as part of an integrated energy savings approach. Thank you for that, and I'll hand over to Steve.
Good afternoon, everyone. My name is Steve Young. I'm an independent power management consultant specialising in voltage management and power quality. So during this session, I'll be going through part of our voltage management assessment process, and I'll be covering some of the key criteria and providing guidance and selection of in how to select voltage management equipment. So before commencing a site study, a consultation should always be carried out to gain a detailed understanding of the client's expectations. If this then leads to the requirement for a detailed assessment, this should be undertaken by a competent person with knowledge and experience of electrical infrastructures, fixed wire testing, power quality, and of course the various voltage management techniques that are now available in the current marketplace. So let's take a quick look at some of these possible outcomes deriving from the voltage management assessment. So in the best interests of the consumer, every possible outcome should be considered, and recommendations should be based on experience, engineering due diligence, and above everything else, the client's site-specific requirements. In some cases, we recommend that voltage management is not viable. This could be down to the type of load-bearing equipment on site or the existing voltage levels under typical load conditions. In another application, the best practice may be to replace the existing transformer with a modern equivalent to reduce losses or to provide an extended tapping range to facilitate voltage reduction and voltage management at the same time. Where viable and where more erratic voltage profiles are evident, then regulators capable of bucking and boosting the voltage can be used to provide a steady, predetermined output, although the reaction times of this kind of technology should always be checked against the characteristics of the supply and any voltage-sensitive equipment on site. It's for this reason why it may be necessary to address existing or foreseeable power quality issues to increase and certainly maintain the stability of the network and the connected loads. However, to be able to successfully identify these issues, a power quality analyzer should be selected over a standard data logger. So let's take a look at some of the advantages of using this kind of data logger. The higher resolution and faster sampling rate provided by a 16-bit power quality analyzer, such as this shown in our new unit here, means that it's more likely to record extreme RMS values. Other than the more obvious advantages of being able to verify compliance with power quality standards, the power quality analyzer will detect short duration inrush currents and the voltage dips which are often associated with these events. Bespoke alarms can also be programmed into the analyzer to capture these and other more complex characteristics. I collated the data in this table here on a site where I actually used both types of logger together at the incoming terminals together, on the LV terminals that is. As you can see here, the results recorded by these units are significantly different, and although the variations can be attributed to relatively short-term infrequent events, misunderstanding these characteristics can lead to the stability of the equipment being compromised. Now this will be covered in more detail shortly, but before that I'd like to run through some of the very basic criteria that should always be looked at as part of the survey. So to do that, I've mapped out a simple schematic, and here we can see the grid supply coming in, feeding into the consumer's 11 kV ring, and then we've got three 11 kV to 4 33 volt transformers, and from the middle one we've attached loads and power factor correction equipment in the middle there. So with all that in place, the power quality meter should be connected at the LV position where the voltage management solution is being considered to be integrated. The logging should be carried out for a minimum of 7 days, but much more importantly than that, it should be carried out during a typical consumption period in order that useful profiling data can be collated. During this period, the site volt drop should be measured so that an evaluation can be made on how a voltage reduction may impact the load-bearing equipment at far points of utilisation on the network. Earth fault loop impedance values should also be spot checked to verify that any reduction in voltage is not going to compromise the values tabulated in BS 7671. And more importantly, the 80% values enforced by some of the third-party accrediting bodies. Perhaps most importantly, in order to calculate the amount of energy that could be saved through a controlled voltage reduction, the proportion of energy consumed by the site's voltage-dependent loads needs to be ascertained. Voltage-sensitive equipment should be identified and considered in conjunction with site-specific load profiles to ensure that they're still going to operate correctly following the integration of the selected voltage management solution. Lux levels in areas where voltage-dependent lighting is utilised should be checked to ascertain if the reduction in voltage is likely to compromise the minimum acceptable lux levels for the particular area of site. Key information should be gathered from existing transformers and switchgear to ascertain capacity and, of course, potential siting of the appropriate solution. So following the agreed monitoring period, the power profiler can then be removed and the data downloaded for analysis. Another advantage of using the power quality analyzer is its ability to properly measure the reactive power and any harmonic interaction between existing power factor correction equipment and harmonic generating loads on the LV network. This is an increasingly common problem and one that's frequently overlooked, but easily identified if the study is correctly undertaken. Again, it's really important to ascertain the proportion of energy that's consumed by the voltage-dependent loads. The savings associated with these loads is of course going to vary from item to item, and understanding how each load will react to a voltage reduction is really the key to assessing the overall viability of the selected offering. Then if a reasonable energy saving opportunity is evident, then a more detailed analysis may be required to ensure that the installation is not going to be negatively impacted through the introduction of that equipment. So to demonstrate this, we've plotted a simple voltage and time chart. The red line here representing a site-specific low limit ascertained from the study. In this scenario, the voltage supply is fairly steady with only 14 volts between the extreme measured RMS voltage values, the maximum and the minimum if you like. This kind of profile is inherently compatible with fixed ratio voltage management solutions, which are generally cheaper than high-tech or dynamic versions. As you can see, the minimum value measured here in the login period is some 16 volts above the site-specific low limit, which means there's some scope for reduction. It is of course important to remember and try and ascertain the optimum voltage or range of voltages that are going to complement the majority of load-bearing equipment at each specific site. Where voltage profiles prove to be more erratic, the opportunities for fixed ratio solutions will begin to diminish. In these applications, voltage stabilizers can sometimes be used, or on-load tap changes. They may prove more viable by reducing and maintaining the output voltage to a predetermined level. In more extreme cases, where the existing voltage profile is already low, for instance during infrequent peak periods, voltage regulators may prove to be the viable chosen solution. Well, by design, these units are capable of bucking and boosting, in other words, decreasing and increasing the voltage to maintain the predetermined set point, even during certain power dips. However, as the automatic reaction time of these units can vary between 50 milliseconds and 10 minutes, and in some cases more, it's important to understand if any load-bearing equipment on site is likely to fail from a temporary loss in power that the voltage management hardware can simply not boost quickly enough. So this can be explained using another simple voltage time graph. You'll note the scale along the horizontal axis now divided into smaller 50 millisecond increments. So let's add in our optimum site-specific low limit, and we can also plot the critical low limit identified by a specific load. And for the purpose of this explanation, we've set this to 206 volts to earth, and using real figures collated from one of our own site studies, we also know that if the voltage dipped below this level for more than 40 milliseconds, a certain item of voltage-sensitive equipment would actually fail and production would be impacted. So in our example, we can see a representation of the voltage dip. This was caused by an inrush current on the LV network. As the duration of the voltage dip exceeds 40 milliseconds, this would decrease the stability of the load and, of course, therefore increase the risk of failures. It's therefore important to quantify this element, and by programming alarms within the power quality analyzer, we can identify the most appropriate solution, including, if necessary, hardware capable of mitigating the risks associated with these conditions. So here we've got some examples of equipment failures that can often be attributed to voltage mismanagement. Unfortunately, some of the more common issues have cast a shadow of doubt and scepticism over the VO market. Historically, these issues have included undervoltage relays for critical systems dropping out, lights failing to strike, and lux levels being compromised in areas illuminated by voltage-dependent fittings, to name a few. An example from one of our recent industrial clients, we saw a site generated infrequent voltage dip below 208 volts. This had a duration of around 80 milliseconds. Now, this was causing a number of CNC machines on site to drop out on low voltage. These machines had a maximum tolerance of 50 milliseconds before they failed, and this was confirmed by the CNC manufacturer. Now, by introducing real-time power factor correction, we could not only improve the power factor, dampening the inrush currents, but the specified solution was able to react in less than 40 milliseconds. Obviously, this increased the stability of the entire process. Another similar example, we saw voltage dips around 206 volts, and they were causing microprocessor equipment to fail. The duration of these frequent events were generally between 50 and 150 milliseconds. However, the equipment manufacturer confirmed that the maximum tolerance here was only around 40 milliseconds. The solution in this instance was an active harmonic filter capable of reacting in less than 20 milliseconds. This solution had the added benefit of being able to mitigate harmonic currents on the network and improve the power factor. Now, the benefit of power quality solutions is sometimes difficult to quantify, but should not be overlooked. It's estimated that power quality problems cost industry and commerce in the EU around £10 billion per annum, while the expenditure on preventative measures is less than 5% of this. That's quite compelling research undertaken by the Copper Development Association. So, how are the savings calculated? Well, due to time constraints today, we won't be going into this in great detail, but the fundamental steps in this process can be summarised along the bottom of the screen. So firstly, ascertain the average voltage reduction that the chosen solution will achieve. Then, calculate the proportion of energy consumed by the site's voltage-dependent loads. Calculate the energy savings that the voltage reduction will exhibit. Then, make an adjustment for the losses associated with any voltage management hardware. This may require adding both no load and load losses relating to an additional transformer, or it may require a subtraction of losses as a result of replacing an existing transformer with a low loss or super low loss equivalent. Viability calculations may require a further adjustment where a client has their own embedded generation, such as PV or wind turbines. And finally, the return on investment period can therefore be calculated by dividing the adjusted savings into the total cost of the project. So with all of this information contained in a summary report, the client can of course make an informed decision. So to summarise, if engineered correctly, voltage management solutions can reduce energy consumption, increase the shelf life of some load-bearing equipment, and improve the quality of the power coming both in and out of the installation. So remember, voltage management is about finding the optimum voltage or range of voltages to complement the majority of the load-bearing equipment without causing failure to any. That's the end of my presentation today. Thank you for listening. I'm going to hand you back to the 2 Degrees panel.
Fantastic. Thank you very much, Steve, and thank you, Erica and Bob, for your presentations. That was fantastic. So we'll go straight into the question and answer session now. And a question, Erica, maybe you want to pick this one up, but someone was asking about what the typical lead times are for transformers, and I know this is something that Bob touched on during his presentation.
Yeah, we actually keep in stock the Wilton E2 up to 2.5 MVA, 11 kV down to 415. So, bearing that in mind, it's about 4 to 6 weeks typically. But if there's any emergencies or breakdown situations, we've been known to deliver within sort of 24 hours. So typically 4 to 6 weeks.
Great, thank you, Erica. Question for Bob. Someone's asking, are you just installing these on new build stores, or are you also retrofitting them to existing facilities?
We're not. Where a transformer needs replacing due to age or degradation, we would obviously use an E2, but we're not generally swapping out existing transformers. It's the capital cost associated with doing that, the intrusion. And obviously the fact generators are required, there's downtime to the store. It's something that's currently not viable. We do keep an eye on that with regards to the current kilowatt hour price, because obviously as that increases, the viability improves. As I say, it's something we have looked at in the past, not currently viable, but that doesn't mean we're not constantly reviewing it.
Great, thank you, Bob. Erica, another question sort of leading on from that is, what's the typical life expectancy of a transformer? And if you're replacing an existing one, what are the options for doing something with that?
Yeah, the typical lifetime, I would say probably 25 to 30 years of a transformer, typically. And if you were replacing one, we usually offer a cost. Obviously, we supply the transformer, and also the transformer that you have remaining, we would buy back, which comes off, obviously, it comes off the capital equipment cost for you. It's off the bottom line. As a business, we actually have a refurbishment part of the business, so we buy back the transformers and refurb them back into the marketplace if it's suitable. So you can have a buyback cost upon a second-hand transformer as well.
Great, thanks, Erica. Steve, I don't know if you want to pick this one up, but someone's asking, will the installation require recommissioning of existing plant in the building?
Yeah, that's a good question. One of the points I made in my presentation was that voltage management is about finding the optimum voltage or range of voltages to suit the majority of load-bearing equipment on site without compromising any. That's the golden rule, if you like. Now, it may be required in some instances that there are small adjustments need to be made to certain equipment on site, but generally this shouldn't be required. It's not about getting the voltage to the lowest possible level. That's not what voltage management is about. It's about finding the right voltage to suit the specific equipment. So usually that won't be required, but in some instances it may mean adjustments to certain controls and relays, and this should be ascertained during the site study.
Great, thanks, Steve. Another question for you, actually. And I know you sort of mentioned lighting during your presentation, but are there certain bits of plant which are more susceptible to lower voltages and voltage fluctuations?
Yeah, certainly. In the case of what you might class as voltage-independent lighting, due to the inertia of those fittings, they're much more tolerant to voltage dips. For instance, we'd be talking about a high-frequency light fitting. The gains from this family of technologies are certainly not there, as they are with, for instance, an old magnetic ballast light fitting. But so your modern high-frequency light fittings and LED light fittings are less susceptible, if you like. And then, yes, of course, that there are certain voltage-dependent light fittings that may start to suffer when you start to drop the voltage down, traditionally to starting to get below around 216 volts. more and more of those old light fittings will perhaps fail to strike somewhere between that down towards 210 volts. That's why it's generally good practice to try and maintain a voltage at load-bearing equipment of not less than 217 volts is good practice.
Great, thanks, Steve. Another question here, Erica, and maybe Bob, you want to add your thoughts to this one, but someone's asking what's the typical payback on a transformer?
Yeah, if you're looking at two different scenarios perhaps, firstly, if you would be installing on a brand new site, so you're looking at the difference in capital expenditure between a standard transformer and a super low loss, you're probably looking at around 18 months payback. That's based on 70% load at sort of 9p or whatever per kilowatt hour. If you're benefiting from, if you're wanting to retrofit and change an existing transformer out and you're benefiting from voltage optimization, clients in the past have had payback inclusive of the installation, the cabling and the monitoring in 12 months. Now, that was an excellent result, so it can be upwards of 12 months, but that's the best result we've had so far. That's for full capital expenditure.
Thanks, Erica. Bob, have you got any thoughts to add?
No, only what I said earlier. I mean, from a business, we have looked at this, but unless there's another associated reason to change that unit, i.e. we're increasing the square footage of the store, but we're extending it, so we need to have a higher capacity transformer on there, which obviously it does happen in our instances where we're doing extensions. In terms of the figures and the CROI and the payback, from our point of view, it doesn't tick all the boxes, but we do have quite an aggressive payback policy at the moment. So it doesn't stand on its own merits currently, from our point of view.
Great, thanks. Erica and Steve, a question for you two is: how disruptive is the upgrade of an existing transformer? So I think in terms of any downtime to the facility operating.
As we discussed earlier, the way that we've designed them, obviously site by site dependent, but we've had situations where the change-out's been done in 6 hours because you've got a flat floor, you've got easy access, you're using existing cable boxes, so you're basically in effect rolling one out and slotting one back in again. So that can be extremely quick. Of course, it can be very varied depending on whether there's switchgear attached or whether it's inside a substation. But those cable heights tend to mean that the retrofits are done like for like, so it's quite a simple operation. Obviously, you just have to assess your site for suitability really and work it out from there.
Thanks, Erica. Steve, have you got anything to add to that?
No, I think that was well covered. Obviously, every site integration is going to vary, and the knock-on effect of that for each consumer is bespoke to each site. So I think Eric has covered the key question there.
Great, thanks, Steve. So I think we've got time for a couple more questions. So another one here. Do you need to get permission from the energy supplier or involve them at all in the process? Erica, do you maybe want to tackle that one?
Well, in most scenarios, you've got. I don't know, Steve, or not?
Well, it's going to vary from site to site. It depends if the consumer's got control of their own HV switch. For instance, if it can be isolated on site. That means that it's isolated upstream of the transformer integration, and therefore it can be handled by the approved person on site. Where that isn't the case and the isolation belongs to the distribution network operator, then quite simply you need them. Hope that answers the question.
Fantastic. Yep, thank you. And one final question here is looking at looking at the power profile for your particular operations, are there certain profiles you should be looking at to gain the most benefits? Steve, do you maybe want to tackle that?
Yeah, certainly. As part of the, hopefully we can pick this up in the initial consultation. Quite often you get to the initial consultation and you can't identify any reason to spend the consumer's money in a site survey, and this could be down to the fact that they've got very low content of voltage dependent loads. In other words, the loads that are going to benefit from a voltage management. That's obviously a very key consideration. Having said that, if they've got their own transformer on site, then the losses are measurable and absolutely quantifiable, and a viability case can easily be put together. But in short, each site can be looked at under its own individual merit.
Brilliant. Thank you, Steve. So that's all we've got time for now, but I'd just like to thank Erica, Bob and Steve for their time today and for getting through so many questions, and also for everyone who joined us for this webinar. Just to remind you all, a recording of the webinar and the presentation slides will be archived on the 2 Degrees platform. So I hope you found today interesting and useful, and that you'll be able to join us for future webinars in the coming weeks. So thank you.
Thanks very much.